Good morning all. Up to now we studied about Newtonian mechanics and Lagrange mechanics. So today we are dealing with the new mechanics, that is Hamiltonian mechanics. So we already have Newtonian mechanics which deal with the forces and motion, and also Lagrange mechanics which describes motion using energy difference. And then why do we need another formulation of mechanics? Do you have any idea? Okay, so the Newton and Lagrange methods are very useful, but they are complicated when dealing with many body problems or quantum physics. And also, in Lagrange uses position and velocity. So it may in many advanced theories require momentum. And also the Lagrange equations are second order equations. So it is very complex to solve. And here from the Hamiltonian mechanics is an elegant and powerful combination of classical mechanics developed by Irish mathematician William Rowan Hamilton in the 19th century. Okay, it provides a new way of describing the motion of physical system using energy rather than forces. And in Hamiltonian mechanics, the central quantity, that is Hamiltonian, h given as h is equal to T plus T. In Lagrange we uses T minus T, but here the total energy. It describes motion in terms of generalized coordinates and corresponding momenta rather than velocities. And also it leads to the two first order equations rather than second order equations. So we can simplify that more simpler. So now we can move to the derivation. We can derive the Hamiltonian from the Lagrangian equation. So what is the equation for Lagrangian? T minus. And what is the Euler-Lagrange equation?
d by dt of
d by dt of rho L by rho qj dot
dou L by 0.
We can write this equation as now qj dot is we can take to another side, that time it will become
Dou L by dou qj.
okay. So we have the conjugate momenta. What is the equation for conjugate momenta? P is equal to
Dou L by dou qj dot
divided by
dou qj dot
dou qj dot. Okay, so we can substitute the value of dou L by dou qj to here. So d by dt of
pj equal to dou L by dou q
dou L by
dou q.
So up to now you understand. First we wrote the Euler-Lagrange equation, and also we formatted equation like this, and we have the Pj, and we substitute the value of Pj into this equation. And now we want to derive the Lagrange with respect to T. We have three terms. We want to differentiate Lagrange with respect to qj dot and T. So that equation will become dn by dt equal to sigma j equal to 1 to n dou L by dou qj into qj dot plus dou L by dou qj dot into qj double dot
Plus
plus dou L by what is remaining?
T.
Dou T.
T.
Okay. So we have dou L by dou Pj. That is dou L by dou Pj is equal to dPj by dt. So instead of this, we can substitute this value. And also dou L by dou Qj dou is equal to Pj. So we can substitute the value this and this as this and this. Okay. dl by dt equal to 1.
20.
Here dou L by dou Pj is equal to dPj by
dt.
so dPj by dt
Into Q J dot plus
plus dou L by dou Pj is equal to
Pj
Pj. So Pj
Qj double dot
Qj double dot
plus
plus dou L by.
dot T dt.
So see the terms inside the bracket. Is there any relation or any specialty for the term inside the bracket? It is the derivative of product. See d by dt of Pj Qj. That is this term. Okay. So we can rewrite the whole term as d by dt of Pj Qj instead of this whole term. Okay. Equation becomes dl by dt equal to sigma j is equal to 1 to n d by
dt
dt of
Pj Qj
Pj Qj
Qj dot
plus dou L by
dot T.
okay. So here also d by dt and here also d by dt. So we can combine this d by dt term. So we will get d by dt of
L
Qj minus
L plus
plus dou L by
dot
dot. Okay, any doubt up to here? So we can take this term to another side, that time it will become
minus
minus. Okay, we define this term up to this. Dou Pj Qj minus L as a function, that is h. Okay, we h is equal to Pj
Qj
Qj dot minus L. Okay. This is Hamiltonian. Okay. Also for h we define in terms of Q, P and T. Here the Legendre transformation. That means in previous time we used with velocity, position and time. But here we are using momentum. Okay. There comes the Legendre transformation. For up to this, we can substitute h. So ds by
dt
dt equal to
minus
minus
dou L by dot T.
dou L by dou T. So if the rectangle is not depending the time explicitly, the term this ds by dt also will become 0 and dou L by dou T also will become 0. This means the energy is conserved. So we can say that in Hamiltonian mechanics the total energy is conserved. And the final equation we already wrote that h is equal to What is the value for h?
t plus c
Delta Pj
q
Qj minus s. So we can substitute the value of l